Welcome everybody. Today we have Vaibhav, who's going to start a new series on quantum field theory, string, Susy, anything that will make sense to understand what is string compactification. So his first talk is on the basics of quantum field theory. Okay, Vaibhav. I will
Okay.
encourage to ask and interrupt him as much as we can. Okay, he will not mind. You will not mind, right?
No, I won't.
Okay, okay.
Okay, so firstly, thank you for giving me the opportunity to talk. One thing I will say is this is meant to be a super, fast crash course. So it's not really trying to replace a traditional course. So the point of this, QFT preliminary crash course is just to sort of get you acquainted with the jargon. So it's not like we're going to be doing, you know, um, the explicit computations, but I really urge you to, pick up something like Sredniki or Peskin and Schroeder and go through those. I have a bunch of notes. If I sort of polish them, then I'll definitely make it available. So, okay, so I'll sort of take it's not going to be very chronological, but it will be, useful because the point of this is, like I said, it's not to replace a QFT course, but I'm going to try to incorporate some of the physicalities into it. So the way we'll sort of approach this is we'll approach this from something that we already do know. So we know gravity, we understand Newtonian gravity, we understand we understand general relativity. And when your background is just flat space, it's Minkowski spacetime, right? So you have four forces, and the interesting thing is that electromagnetism, weak and strong nuclear forces, these can be understood in a quantized fashion much better than we understand gravity. But the way we'll sort of want to approach this is, understanding quantum field theories on a background, not just ordinary quantum mechanics. So the idea is that you have a four-dimensional manifold. So just to sort of remind you, space-time is, I'm not going to write too much, but it's a four-dimensional manifold. So M is your manifold, G is the metric on it. And it's a pseudo-Riemannian manifold. So the metric signature is going to be negative plus plus plus. You can alternatively try plus minus minus if you feel blasphemous. And the thing about this approach is that you have loads of data. So the data on this space-time would be your metric. It would be matter fields on it. It would be the cosmological constant if you're working in, let's say an anti-de Sitter space-time or a de Sitter space-time, higher corrections, etc. So for now, we'll ignore both of these. So we're working in a Minkowski spacetime, so lambda is equal to 0, so there's no cosmological constant, and we don't have any higher derivative corrections or anything of that sort. So this is just ordinary vanilla general relativity. Now the question is, how do you make sense of fields on this? So one of the important things about quantum field theories is that, it's important to understand the foliation of spacetime. So when you say I have a quantum field, it's usually meaningful to talk about it given a Cauchy hypersurface. So we assume, and I'm going to mark this with a star, we'll assume global hyperbolicity, which means that my spacetime can be written into a series of Cauchy hypersurfaces. And this foliation sort of allows you to, have quantities that you can sort of concretely measure or, compute. And it inherently also tells you, what evolution looks like. But of course, in quantum field theories, there's a lot of subtleties around, sort of the picture, but we'll get there in a second. So, for instance, one of the things we can do is we can take a Cauchy hypersurface. So I have that, which is my sigma. So this is sigma at some times equals, let's say, T0. And let's say I have some region, which I'm going to call U. Now the question is, given this region, what do I know about a field on this? So at sigma t equals C0, we can identify fields so that these fields, which are functions of space and time, are fixed. So this is at t equals c0. So given these fields, what can I concretely observe about this? So what are the things we want to compute? These could be things like the Hamiltonian, the energy, or the vacuum energy, or interactive field correlators, or S matrices. So we'll get there in a second, but the ideal thing we want to do right now is to arrive at a definition of what field theory is in a manifold sense. Now this is, this could just be, for instance, just ordinary electromagnetic fields. So when you quantize an electromagnetic field, it just becomes a theory of quantum electrodynamics. And you use things like Feynman diagrams, but the essential idea is still the same thing. So the essential idea is still that you have an electric field, let's say, and this is associated to all of U. So for every single point in U, so for all points in U, we have some associated number, which sort of tells you something about the field. Now it's not really a number in the conventional sense. For instance, there's a direction. So if you took the famous example with iron fillings, and you just put for instance, let's say a magnetic field on it, then this would be magnetic fields, and for every single point, we're going to have essentially two numbers. The first number will tell you what direction the field is pointing to, and the second number will tell you how strongly it is pulling you to it. So this is just your ordinary iron fillings example. But of course, in our case, that's not, our example isn't in R3. It's actually going to be in a theory, which is relativistic. And one of the ideals of starting with, Minkowski space is that you don't have to worry about a background. It's not really easy, but, topological quantum field theories are usually simpler in a sense that, there's no background to work with. Otherwise, you'd be working with locally covariant quantum field theories, which are significantly more complicated. So our idea is, you have some region in space-time and you want to do, field theory on it, and you want to quantize it, and, you want to make some concrete, computations. Now, a very simple example, which is, as elementary as it gets, is you take a Lagrangian for a free real-valued scalar field. Free in the sense that it's not interacting. And it should be obvious from the way that the Lagrangian is written, because the Lagrangian is something of this sort. So eta is the Minkowski metric, d mu phi plus m squared phi squared. So I'll get here in a second as to what this really means. But so when I say d mu, I really mean the derivative with x mu. And if I say d mu, I really mean derivative with x mu.
Yeah, there the nu will, on the second nu, it will not be subscript, yeah? It will be superscript in the Lagrangian.
Sorry, which one is this? This one?
Yeah. This will be superscript, not subscript.
Oh, for the mu's and nu's, you mean? Okay. Yeah, I see what you mean.
mu, yeah.
Okay. But yeah, essentially you just want to, solve for the equations of motion for this. So if you construct the Euler-Lagrange equations, again, I won't get into the details of all of this, but if you construct the equations of motion from the Euler-Lagrange equations, what you would do is you would get some equation that isn't really a quantum field description yet, because we're not really doing any sort of explicit quantization, but that will look something like this. So actually, I'll sort of try to be a little more elaborate. So I'll just use partial instead, plus m squared phi equals 0. So this is the Klein-Gordon equation, and this is, in most of the cases, this is just a reduction to relativistic field theory, but we're not really saying what is quantized yet. So we haven't really, told you why this is supposed to be a form of quantum field theory. And quantization here is in a sense, akin to going from classical mechanics to quantum mechanics, where you take Poisson brackets and you promote those into commutators. But here, instead of dealing with just this promotion into commutators, we also specify operator value distributions. So the way that we take position and conjugate momenta in promoting a classical theory into a quantum mechanics theory, we will do a similar thing with the field position and momenta pairs. And this is essentially just canonical quantization. So what you would end up with are
Here,
commutator.
your scalar fields are just classical fields.
Yeah.
Oh.
So you would end up with the canonical commutation relations. So I'm just going to try to see if I can. Oh, is the pencil not working? Oh, okay. So the canonical commutation relations would be, let me just get some space, phi x. Oh, okay, so I'm just going to make a notational thing really clear. So here, the capital phi and small phi are sort of interchangeably used, but later on, if I use a capital phi, it means it's an interacting field. But that's just for now we know what the Lagrangian is, so we're not going to specify. There's no real difference here. Okay. So the first condition is really just saying that if you have space like separated points, then the commutator vanishes, and that's equal to 0. The same thing goes with the conjugate momenta. So if you take that, that's equal to 0. And you would have a second relation. So this is just the first pair. The second one would tell you if you take the position and the conjugate momenta commutator, then you would get a three-dimensional Dirac delta function. So that's the sense in which you end up with a distribution. So if you have phi x and pi y, then if x minus y is equal to 0, is not equal to 0, then let me just write this in. Okay, so here x and y are space-like separated, but this only works out if x is equal to y. And the same thing goes over here. So if x is so one interesting thing about this, this particular causality condition is that this will seem to be violated when you're writing down a propagator, because if you have a propagator from x to y for x and y being space-like separated, it will not vanish. But the fact that it doesn't vanish doesn't mean that it's violating causality. In reality, what's really happening is you have time ordering, and if you don't have time ordering, it sort of just doesn't make sense, because that's the sense in which you write down the propagators for causally connected x and y. If they're not causally connected, then it still is in satisfaction of the causality condition. And in this setting that I just explained, we don't have time dependence. So the evolution equation is really just the Schrödinger equation. But in contrast, the Heisenberg picture would assign time dependence by evolution operators from H. So that would, so let's suppose we had an operator x t, that would, sorry. So that's the Schrödinger picture. In the Heisenberg picture, what you would basically have is, if I have some operator, let's say x and t, then that will be equal to IHC. And again, another conventional, I probably should have made my notations much better, but so when I say this and when I say just x, I typically mean the same thing. So if I explicitly say x arrow, then I would be particularly just talking about the spatial coordinates. But in this case, it's really just x. So yeah, I'll just leave that. And then the operator, and then you conjugate it. Now, again, like I said, I'd add, I would typically be adding an arrow to represent spatial only dependence. And similarly, you can take the equal time CCR. So it would be similar to these two equations that we've just gotten over here. So these two equations that we've gotten for the Schrödinger picture, you could get for the Heisenberg picture, taking equal time dependence. So in that case, the equations would look similar, except you'd have to specify a particular t. So again, this picture will be clear depending on the setting of the discussion, but for most cases, we will, solely be working with the Heisenberg picture. Okay, so again, coming back to the question of what do we really want from a field theory? So from quantum mechanics, we know that observables are the things of interest, right? So given a Hilbert space, these are our Hermitian operators, and we want to define some observables for this U. So for the bounded region in spacetime. So a field theory is typically, again, like I said, it's of interest when you have when you have, again, I'm assuming global hyperbolicity, when you have a Cauchy hypersurface and you have, some region, and now you could ask loads of, all sorts of questions. So you could ask, what's the entanglement entropy, for instance, which is, of course, that's, it's a very fascinating question. Or you could ask, if I have an interacting field theory, then, what are some, let's say some 2-point function or something of that sort. So, so the object of interest is assigning to this bounded region some algebra of observables. But how much we actually end up using it, it's not really
I
it's
have a
not
question.
okay.
What do you exactly mean by an observable? What qualifies an observable for you?
So an observable is really just it's really just a Hermitian operator. So for instance, if I have the
It doesn't
if I
have
have
to be
the
Hermitian, right?
yeah, I think you could have
You
pseudo Hermitian
restrict the
operator.
algebra to Hermitian when you talk about von Neumann algebras, but observables need not to be Hermitian, right?
Yeah, I'm trying to be just a little textbook because, the way that most textbooks start is, it's just, you start with observables that you already sort of are familiar with. But yeah, it doesn't have to be Hermitian. In fact, I think
No,
one of the
so
motivations.
my question is like, let's say if you have somebody on world line, right? If you have an observable, like if you are on a world line, let's say of some particular theory, and you are observing things. So let's suppose you are talking about Hamiltonian, yeah, it's a Hermitian operator we all know in quantum mechanics. You are calculating the Hamiltonian, that is to say the energy of the system. So you call that an observable, or you yourself are an observable?
Yeah, that's one of the reasons why I was very clear not to mention the Hamiltonian as an observable for now, because, yeah.
No, because see, the
I,
thing is that many people talk different things when they mean observable. Some might say that it is just an operator, some might say no, it's an observer itself. That's why I was asking you, what does it for you like?
yeah, I'll just say it's an operator, no observers. I'm not going to talk about what an observer is or what it isn't.
Yeah, right.
Are there any questions from okay, again, just to be clear, you don't need to worry about what an algebra of observables is. It's just, it's of interest. You just keep it in the back of your mind because if you were trying to be very concrete about, quantum field theories, you'd have to do a lot more than just, say a QFT is an operator value distribution. But there's many senses in which you would approach QFTs for different reasons. So, for instance, you could approach axiomatic quantum field theories from functors or from algebraic quantum field theories, which is where, algebra of observables and those sort of things, or von Neumann algebras, like I just mentioned, pop up, or, topological quantum field theories when there's a background dependence and stuff like that. So, yeah, there's many different, senses in which you would use, the word, QFT, but, for now we're just being very grounded, right? So,
Yeah,
okay.
if I may add a comment, right? Can I?
Mhm. Yeah, sure.
Yeah, I'll speak in a very Carl Sagan way. So when physics started, it was all sort of like waves and all, basically
Mhm.
waves. Sometimes later it became particles and all. So
Mhm.
this kind of duality is very confusing, right? So what to
Yeah.
do when, and That's where quantum field theory jumps in. It provides a way to talk about two things at once. So when you have quantum field theory, the quantum mechanics, it's more of like a duality, but in quantum field theory, it just becomes fields. So fields are fluctuating, and then you are getting your particles, your waves, or whatever you are saying. That's just when you do classical electromagnetism, you have these two fields, right? Electric fields and magnetic fields. Their oscillation produce electromagnetic waves. And when you quantize those electromagnetic fields, you will get some other things like, right, for example, photons. And these
Mhm.
photons will have the causalities of electrons and protons and other sort of charged particles. So it is really important uh, to think of quantum field theory historically as a built-in for understanding this wave particle duality. Yeah. So
Yeah, I think that's a great, motivation. Yeah. And, I will also add on that, which is, QFTs are also much more, they're sort of much more stranger to work with, of course, because, the moment that you go from, quantum mechanics to quantum field theories, your degrees of freedom are infinite. So there's no, sense in which you're constraining it as of yet.
right.
So because of that, if you try to do like even if in the case of a bounded region, it is still infinite volume, which is why you end up adding in, lattice, cutoffs and stuff like that. So yeah.
And that is why mathematically it doesn't make sense to understand because of this infinite entanglement between points, right? These degrees
Mhm.
of freedom.
Yeah.
Yeah.
And as if to, sort of make it a point to bring up one-dimensional algebras again. Yeah, so one of the reasons why one of the reasons why quantum field theories on general quantum field theories really, why they're hard is because they become type 3 algebras, in the sense that, you get infinite modes of entanglement and that sort of yeah, and when you add in a lattice cutoff, it sort of becomes, you know, um, something that sort of factorizes. Okay. So like I said, it's not always going to be in your, it's not always going to be in your interest to just talk about, fields at one particular point. So you could have, a very simple example is, I have, let's say, an experiment where, a particle is emitted at X and it's absorbed at Y. So now, how do you talk about, this probability amplitude? And, as we'll go on, we'll also see that, this is also where the intuition towards, excuse me, this is also where the intuition towards, interaction diagrams and path integrals comes from. So, okay, so let's suppose we take, so another piece of convention. So I'm going to go back to black. So this will be my free field theory vacuum. And when I say omega, that would be the vacuum for the interaction picture. It'll be clear in a moment what I exactly mean by that, but just bear with me because we haven't really come up to what it even means to have interaction terms in a Lagrangian. So, we'll get there. But the idea is, if I have, such a simple experiment, how do I exactly compute the probability of that? So technically, all you're really trying to compute is, something of this form. So you take the vacuum state and you have phi x and let's say phi y. So x and y are points, and we'll say that they're causally connected for now. By which I mean that y is in the future of the past likelihood of x, where x and y are now. So this is what I was talking about earlier, which is, if X and Y are acausal, or if they're causally disconnected, or they're, connected by a space-like curve, then the propagator won't exactly vanish. But the sense in which this works is if you add in a time ordering symbol here. So because I said, it's absorbed, it's emitted at X, and it is absorbed at Y, I'm technically adding in time ordering here. So when I add in a time ordering, I'm really just, computing a Feynman propagator. So this, which I'll represent by, oops, sorry. I'll represent this by just a delta. So this is just going to be delta x minus y. But when I add in time ordering, I'm actually just going to be computing a Feynman propagator because, we're inducing time ordering between the way that I'm computing phi x for phi y. So the Feynman propagator, which I'll denote with delta f x minus y, is then going to be that. And so t is the time ordering symbol. So let me just write this down real quick.
It might be helpful to introduce propagators, right?
Yeah.
Briefly.
Yeah, I'm really just saying, we're just constructing a simple, absorption emission, experiment. So,
Mhm.
but yeah, I think one, okay, I'll leave that
Maybe a
for,
good way
any
to
other.
do is to the Feynman diagrams, you know.
Yeah, I'm constructing them in, I think about, 5 minutes or something. So yeah, I'm right there. So by time ordering, what I really mean is, phi x, phi y would be either phi x, phi y, or phi y, phi x. And let me just move this here. If x is greater than or equal to y, and if y0 is greater than x0. So by x0, again, this is a notational abuse, but by this I really mean that if x comes earlier, then it's going to be phi x, phi y. If y comes earlier, then it's going to be phi y, phi x. Soon enough, we'll also encounter normal ordering, but I actually won't be talking about it particularly well. And the way that you compute these is using some, tedious contour integration, and you add in some pole shifting, tricks, which is actually an important trick. In hindsight, I probably should be talking about it, but, you add in the I epsilon, term, and you solve it in the epsilon goes to zero limit, and that's how you evaluate the integrals when you're doing these propagator or correlator calculations. And so the example that I just gave for the Lagrangian above is there's no interactions, it's just a free field theory. And the Hilbert space of this is just going to be take the vacuum and take the multi-particle excitations on top of it. So that's what you call the Fock space. Now, if you want to have any interactions, which is of course the case for any physical theory, you would add in terms that go beyond the quadratic term and the potential. So then your Lagrangian will be that d nu phi plus m squared phi squared plus other terms starting from n equals 3. And so again, this, we're not really going to be evaluating anything immediately yet, so don't really freak out about this. But the idea is that this is just a power series for the interaction Lagrangian, and this is the potential term. So this is really just the potential. You can take in different orders of this. So you could take n equals 3 itself. So that would be to add in 1 over 3 factorial G3 phi 3. So that's going to be your cubic theory. Or you could go, phi 4, etc. Or I just one thing I have to. Okay. Should we
Yeah,
wait or
let's wait for 1 more minute and then we can start.
okay?
Yeah, just one more comment. We talked about Fock space, right?
Mm-hmm.
Yeah, yeah. Maybe we'll confuse it very much, but Fock space is just Hilbert space, right? It's just a Hilbert
Yeah.
space with infinite separability. You have infinite number of particles in quantum field theory, right? Infinite number of degrees of freedom. What you can do is just have a direct sum of those Hilbert spaces, and then
Yeah.
do the superposition of those. So it's nothing. You just have a separable Hilbert space. Uh, so Fock space has this separability.
Mhm,
Yeah,
yeah.
and
In
Hilbert
hindsight, I
spaces.
actually creation and annihilation operators, but yeah.
Yeah, those are important to understand those things, right? The Fock space.
Yeah, yeah.
It's more of a tool to understand the infinite. Sorry, it's more of a tool to understand the infinite particle paradigm of the quantum field theory.
Mhm, yeah.
Otherwise, you're just dealing with Hilbert spaces in even in quantum field theory, and that's what you
Yeah.
should mostly think about,
Yeah,
right?
because I think yeah, because one of the important things about doing quantum field theories is that you construct
Hmm.
commutation relations for annihilation operators. The way you define a vacuum is in that sense. So yeah. Uh,
Yeah, and that is why it's very important to when you are learning quantum field theory. It's very important to play around with vacuums. So the vacuum that you play with are very important in quantum field theory. Basically, you're solving the equations of motions for them.
yeah. Yeah, again, I think it would be optimal if we have like, some rough notes and we could just, have some references and, handouts or something like that.
Yeah, let's think of that. Okay, you can start, Rob.
Okay, so now the thing about the interaction, an interacting field theory is that of course, it's going to be much more complicated than a free field theory. Um, and one sense in which that is so is, what you make of the picture of it. So earlier we saw the Schrödinger picture, then we saw the Heisenberg picture. The interaction picture is a little more, it's more of an abomination. It's a sort of imitation of the Schrödinger and the Heisenberg picture. So one of the things you would do is, you would take the Hamiltonian and you would decompose it into something that, goes with free field theory. It's again, this is an approximative way of talking about this, but you can bear with me. Plus some term that tells you um uh the sort of the interaction modes on top of that. And um so again, this interaction picture, it has a lot of subtleties, but one of the nice things you can do about all of this is okay, I'll just give you an example. I think that's just easier. So for instance, if you constructed an S matrix and you wanted to, if there was like a black box scenario, so you have an in state, so it's X and T, and you have an out state, which we'll say Y and T. T prime. Okay, I won't bother you with that, but okay. So in this case, I could ask you what's the transition amplitude for this? And if you're trying to find out the transition amplitude for the in and out states, it's really just a sort of a correlator computation because of something called the LHC reduction formula. So if you wanted to solve for a two-point function, so if you wanted to solve for this example I gave here, if you wanted to solve for this with time ordering, then you would use this Hamiltonian decomposition and you would basically redefine your field definitions. So this is what I was mentioning, way back when I said I was abusing notation. So now I'll use capital Phi for the interaction picture. So what I'll do is I'll take phi interaction t, and I'll define an evolution operator here with respect to h0 of t, and then your classic your ordinary field, and um, so this redefinition also goes with it also applies, identically for the conjugate momenta. And the end result is you want to find a vacuum for H0, which is just going to be your usual, it's just going to be your usual your vacuum. But if you add in the interaction terms theory, then you would end up with a vacuum that would look like that. So not only are you trying to compute correlators, you're also trying to, find out exactly what this vacuum is. And you have to expand out this evolution operator. So what he would do is, define a time evolution operator, and it would basically be conjugation with IH0 and the interaction Hamiltonian. And you sort of do some clever tricks with expanding it out. There's a bunch of tedious math, but the bottom line is you can get the interaction vacuum in terms of some sort of a transition. So what you could do is let me just take in a red colored thing for this. So this is the vacuum of interest. So what you would do is you would try to compute should I go X or X once? Okay. And then Y. And then minus H, I think it should be interaction T over oh, sorry, I'm just going to erase this. So, how do you make this bigger? Oh, minus I, H, I, C, T. So again, we're still going to be using the I epsilon trick, but the idea is that this 2.4 later is, that's what you're computing for the interaction vacuum and the ordinary free vacuum. So, but this doesn't really get you anywhere yet because you're still trying to evaluate the time-ordered field insertions. So that is still the task to be done. Now, if that is indeed the case of, so what you can do is you can take in the normal ordering of different sort of contractions. So this is sort of where you get the idea of interacting, field theories and interacting diagrams. So interaction diagrams. So if I'm taking the time ordering and I take, by n, then adopting normal ordering, which I won't go into right now, but you would take in contractions once you take that plus distinct contractions over pairs. So now what does this mean? So let's suppose I had a 4-point function here. So there, and I take phi1, phi2, phi3, and phi4. And I was trying to evaluate this. Then this would decompose, and this is because of something called Wick's theorem. So this thing that I just told you over here, this is really just Wick's theorem. So let me just box it. Okay. So now what Wick's theorem is really telling you is that you can just evaluate contractions with the Feynman propagator for different distinct pairs. So if I have phi1, phi2, phi3, and phi4, then what I would have to compute is really just phi1, phi4. And then I would have to add in, I'll just add in normal ordering. So the square bracket is normal ordering. I'm not really going to write n over and over again, plus the contractions over it. So the contractions here would be taking phi1 and phi2. Plus phi1, phi4, phi2, phi3, and other contractions. So by this contraction, I mean I'm contracting this pair into a Feynman propagator, keeping everything else, unchanged. So when I do that, this decomposes into 3 pairs of Feynman propagators. So that would become, let's see, x1 minus x2. Okay, there's someone selling stuff, I guess. Can you hear it, or should I just mute for a second?
No.
Okay. So that's going to be, let's see, 2 minus 3. Sorry, 3 minus 4 plus plus, let's see, it should be x1 minus x4, x2 minus x3. Okay, so these are going to be your Feynman propagators. So, there's two pairs for each term. And so when I write this down, I want you to basically think of these as being interaction propagators for different points. So if I have x1, I have x3, x2, x4, then the first term that you see over here, so this term, this is the first propagator pair. And what it's telling you is it's going to be this. So it's going to be x1 and x2, and it's going to be x3 and x4, because those are the propagators. And then, I keep forgetting to switch. So that's going to be x1, x2, and x3, x4. And then for the second term, it's going to be x1, x2, x4. It's going to be, let's see, it's going to be x1 and x3, and x2 and x4. And for the last term, it's going to be an x, so x1, x2. So it's going to be that and that and that and that. So it's going to be those. So these are the three diagrams which sum up to computing, this 4-point function. So this thing that we were trying to compute, this is really just going to be the sum of three unique interaction diagrams. So this idea of contractions really just give you, Feynman propagators, and these Feynman propagators give you these interaction diagrams. Okay, that's good. So I won't go into Feynman rules or, actually drawing the Feynman diagrams as of yet, because I think, there's some things that I would want to cover. And, I really want to just, go over one thing really quick, which is the idea of using path integrals. But ideally, when you're constructing Feynman diagrams, you would sort of, go through the rules of, how it is that you expand on the integrals and, stuff like that. Is there any question that I could answer? Okay. So now the idea of a path integral is important. So there will be a lot of clarity, and I think around the next lecture, because right now my point is just introducing a bunch of things that you'll sort of use in the next 2 lectures. So for instance, what do you make out of Feynman diagrams? It'll be a lot more apparent in the next lecture. Oh, I don't think I'm giving it. I think Ayush is giving. Would you cover Feynman diagrams?
I will.
Okay. So yeah, that'll be a lot more apparent in the next lecture then. But one thing I really want to quickly go over is that the idea of constructing these transitions, it also naturally gives you the idea of path integrals. So when I talked about the evolution operator, you could ask, if I have some state, and then if I have some state at t equals t0, and I have some final state at t equals capital T, or something like that. So if I have, let's go back. So let's suppose I have some state. Okay, I'll just use, what can I use? Q. So let's suppose I have Q final and T final, and Q initial and T initial. And I asked you, what's the effect of the time evolution operator on this? One really interesting thing that sort of pops up is the notion of a path integral, because you can split, the start and the end times into, some segments. So basically, you could cut that into a number of, into, let's say, n segments, and then you take the limit in which n goes to infinity. And typically, what this would mean is you would construct, terms which, let's see, so that would be amplitudes for, let's say, Q final, and then you would take some, so let's suppose that we take some delta T cut. So that's going to be IH delta T. and we take in the state before that. So instead of Q final, it's going to be Q final minus 1 times Q final minus 1 delta T, and then Q final minus 2, and so on and so forth, until you end up with Q2. I think I had T I. Okay, I don't know. So it's going to be that IH delta T and Q1. I'll just choose one. Now, the thing about this is also that, when you write down the if you actually wanted to solve this integral with with all of these individual pieces, so let's suppose there's j pieces of qi of qj, so then the measure would be no, it's going to be the product with dqj. But if you actually wanted to calculate this, what you would have to do is you would have to decompose the Hamiltonian, and you would use the Baker-Campbell-Hausdorff formula. It's a bunch of stuff, but at the end, what you get is it's going to be the first look of the path integral in quantum mechanics, right? So it would look something like dq. This is d. Okay, so this is just d. J and ijk dp. So, and then you would have the exponential terms. So it's going to be I could be wrong about this. I could miss something up. So this is k. So times delta q j, and then I h of delta t. So now the h is going to be in terms of it's going to basically take two states at once. So it's going to be, let's say you start with q final minus 1 and then q final. Then the Hamiltonian will take in those two terms. So it's going to be it's basically going to how do I put it? You get the idea, though. It's essentially, you have to expand out the integral in terms of the terms that go with qj. So you take subsequent j's, and then you take pk. So the end result of this is that this is sort of a path integral. So the sense of this becomes, say,
No, nothing.
Okay. So the sense in which this becomes a path integral is you define a sort of collective measure for q and p, and then you sort of put all of the exponential terms together. So for instance, the way that you calculate, let's say, the vacuum function is going to be in terms of, so this is just going to be so let's suppose we take in sources, which I'll label with j. This is not a subscript, I'll just put it in brackets. So if you wanted to find out this amplitude, then this would essentially just be, taking in the fields. So this would take in all the fields. So this is the path integral measure now. And then the exponential of t4x. And then you take in the Lagrangian for the free field plus those with the sources in them. So the idea of this path integral is that you sort of write out a very super chunked measure, and what you'd end up with is a product measure, and that product measure is essentially the d that you see here. So this capital D is essentially just signifying that. Now, what's useful about this is you can use this to compute correlators. You can use this to solve for interacting field theories, but a lot of that will be covered in once we sort of have a suitable understanding of what Feynman diagrams are.